Thank you for coming along to a really in-depth talk near the end of the day. Good job there was a coffee break before this one, I think. My name is Matt Warren. I sometimes blog at mattwarren.org and I work at a company, if it wasn't at all obvious. I'm happy to wear the free t-shirts they give me. I work at Contrast Security and we do security tools for developers. And part of why this interests me, because it overlaps with my day job and some of the things I get to do there, which I'll go into a little bit later, but generally we provide tools for you to analyse your code and see if there's security issues. That's what Contrast is about. But this talk is about performance in the .NET runtime. I should start with, I guess, a disclaimer up front. I love this stuff around .NET internals. If it wasn't clear, if you read anything on my blog, I'm more than happy to spend quite a lot of time figuring this stuff out, just mostly for the fun of it. Some of it, as I said, overlaps with my day job, but a lot of this is for information. And it's been quite good over the last few years because basically they open sourced the .NET runtime back in 2016. So we can dive into this stuff. You can get, if you're really keen and you really want to, you can build your own version of the runtime and run it locally in debug mode just for the fun of it. But more seriously is that we can find this stuff out. It's a lot easier. Trying to do some of the things I do to research talks like this and others 10 years ago would have required some sort of ninja WinDBG skills and a level of assembly that's beyond me. But I really like this stuff and I really enjoy digging into it, and it seems like people respond to that as well. But I think it's easy to say, I like this stuff, but maybe put my money where my mouth is. This is my collection of books. As far as I know, I've got one of every book that ever come out that talks anything about the .NET runtime internals. And there's a few that aren't here that I have ebooks. So at some point stopped collecting physical books. But anyway, this is quite a good set of resources if you want to know more about. Often it overlaps with performance actually, so some of the books are talking about getting performance, but mentioned. So this is a good list. The one that's missing here in a recent one I'm reading is the 1,000-page book about it's called Pro.NET Memory Management. If you want to learn anything about the .NET GC, it's covered in that 1,000-page book. But anyway, there's a lot of good resources out there as well as blogs. So yeah, I really like this stuff. But maybe a bit more of a justification for this. It's not just because I like talking about it and hopefully other people like listening to it as well, but actually there's a level where understanding one level below what we're working from is useful. So it quite often comes up in performance. If you want to get the most performance out of the CLR, the runtime, you do need to have an idea of what the JIT is doing or the garbage collector is doing. You need to understand which things are more costly than others. You also need to measure, and all the other sort of general advice. This is not a performance talk in that sort of way, but you need to measure these things. But actually there's times, isn't there? I'm not going to stand here and claim that day in, day out, knowing what's going on in the runtime is affecting our jobs. That would be a bit disingenuous. But I think for a lot of us, there's times where this stuff comes up. I think also it's good that as a kind of wider community, it's not just the people at Microsoft who work on the runtime that know these things. I think it's good that actually it helps our ecosystem. It helps us have better libraries on .NET, or it helps, so this general understanding of what the runtime does. The promise of the runtime is that we can treat it as a black box, and yes, that does apply. We just write our C#, F#, VB.NET code, whatever language we're writing, and then the runtime does its thing. But actually there's times when it's worth knowing one level below your usual abstraction. And of course that can vary. So sometimes that usual abstraction is, you're working on top of ASP.NET, so you need to know that. Sometimes it's the base class library. But I think for a lot of us, there's times where actually knowing things about the runtime, how delegates work, or why certain types of method calls are more expensive than others. And as I said before, it often comes up with performance. To get the highest performance out of the runtime, knowing these things is useful. So there's a lot of things in the runtime. To give a bit of scope to that, I did a previous talk which was called From .NET Run to Hello World, the simplest program you can do. That's a 45-minute talk, just talking about everything that happens from the point you write .NET Run to the point that Hello World appears on the screen. And that, if you know anything about those sorts of applications, a very small application misses out a lot of the stuff that the runtime does. There's probably no time for a GC to happen, and a few other things that I'm deliberately missed out. So there's a lot going on in the runtime. It's a huge Piece of engineering is a huge piece of software. There's a lot of stuff going on there. So to give a bit of focus, I'm just trying to do the overlap, the intersection of some things that are going on in the runtime that are designed or written or implemented in a way that give us performance. So we get to use the runtime, we write our code, and there's a lot of things that actually happen to not just a naive way. There's a lot of work that's gone in to make things that we would expect, to be fair, from a runtime, to be quick, but there's a lot of work to make that happen, and we'll talk about those. One of the ones is maybe methods calls. We don't ever really think about what's going on with a method call. That's fair enough, the runtime handles that for us. But it's not an accident that .NET can work in high performance situations, tech in power and things like that, if you've ever seen those benchmarks. And a lot of work goes into making even something as simple as a method call efficient. So, but just to give a kind of overview of the landscape, if you like, I know that not everyone has delved into the code of the runtime or knows some of the components and things like that. So this is probably, I think, I think it's pre-COVID. So anyway, that makes it a couple of years old. So you could probably add 10% or 20% to these numbers, but it gives you an idea, right? There's a lot of code in there, over 2 million lines of source code, 8 million lines of test code, which is, I think, is not a bad ratio for a runtime. You'd hope that they'd be testing quite well. This is what's considered the core runtime. The base class libraries are separate from this, so these numbers go up if you start to include all the, the base class libraries we know and use every day, the collections and all the other things that live in system and Microsoft namespace. This is the core runtime, can actually run standalone, can't do too much more than just a Hello World app with the core runtime. You do need the base class libraries to do anything more useful, but this gives you an idea of the scope of that. Lots of files of source code. There's quite a lot of C# code in there, although a lot of that is test code. By far the bulk of the runtime is written in C++, which may not be that surprising. Quite a lot of IL code, that's generally for testing. The runtime wants to be able to test in different scenarios without necessarily having to rely on the compiler. So it has its own, it goes directly from the IL code, because that's at the level the runtime works. We write our C#, F#, whatever code, that gets turned into IL, and the runtime then does the job on the IL code. Bunch of assembler code, and we'll look at some of that later on. A bit of Python and Perl, I believe, is for scripting and test, supporting code. I don't think any of that, or none of that ends up in the runtime itself. But the point I want to get across is there's a serious amount of gone into this. And the open source Core CLR, it's mostly known, although it's now, they changed it, .NET 5 just became .NET rather than .NET Core. But anyway, that runtime has not suddenly appeared as an open source version. That's come from the heritage of .NET all the way back to the beginning through Silverlight and all the different versions. So it's not just code that suddenly appeared, 2016, 6 years ago. It's built on all the code. And in fact, some of the code goes way back to the very beginning. Some of the low-level internal things don't change. They might have improved certain parts, but there's parts you can trace back. And one of the books I showed a minute ago is about something called Rota. And Rota was essentially the runtime that was open sourced about 20 years ago. It was under a sort of academic license, and it roughly equates to the .NET 2 timeframe. And you can look at the source code of Rota, and you can see some similarity, at least in the file names, maybe not completely the content of the file, but there's things that have stuck around since that point. Maybe a more pictorial way of looking at things. These are just square maps, just basically the size of the source code in those folders. And these folders are not just the source code folders on disk, but they're kind of the naming terminology of those components as well. So it's fairly well structured and split up like that. So to go through some of these, MS Core Lib is actually now system private core lib. This is the C# code in the runtime. This is things like system.gc. There's a rule about this part of the code that it can't have any dependencies. So anything this code needs to run has to be in there. So that's why some collections are in there. Obviously the core type string and some of those are implemented in there. And this is, and then reflection is another one that sits in there. So it's kind of very core parts of the component, the bits that are needed to do anything at all, the bare minimum, if you like. But the reason why that sits in the runtime and not separately is because that, say we take the example of system.gc, right? The APIs in system.gc need to match exactly what the current version of the GC is doing. So that's why this is shipped as part of the runtime, not as a separate thing. And there's some special rules. Like I said, it has to be the first thing loaded. It can't, and certain types, strings and arrays, as we can sort of imagine, are quite special types. They do quite special things. So the runtime needs to know that the code in here is matching what the runtime, and there's certain things that this can do that other codes, in terms of knowledge, this code might have that other third-party or even base class libraries can't have that same knowledge. The JIT, just-in-time compiler, is a huge chunk as well. The code that's responsible for taking the IL that's come from the compiler, the C# compiler, Roslyn compiler, and then JITting it the first time it's run. That has to worry about generally different CPU architectures. You know, it's JITting code for all the platforms that .NET runs on. So x86, x64, ARM64, and some other ones I've forgotten. Anyway, there's quite a few, and they're growing over time. And so there's obviously per CPU architecture knowledge in there. There's, functions are written multiple times to support different things. It has to have a knowledge of registers and lots of things. There's a lot of complexity in there. The GC is a relatively standalone component as well. There is actually a way you can run the GC. If you're really keen, you can run the GC separate from the runtime. And also, in theory, you could implement your own GC and drop it in as a replacement. There's an API and an interface it sits behind. Probably the most thing people know, or the most interesting thing about the GC is it's basically one single file, gc.cpp. And for the longest time, if you looked on GitHub at the file, it would say too big to render. So there's historical reasons. Maybe they like the idea that it's one file. Who knows? I wouldn't fancy working on a 35,000 line of code file, but anyway, that's the way it is, and it's probably not going to change. It's been part of the runtime from the beginning. Another bit that's always surprises me is just how much goes into debugging. So if you're in Tess's talk this morning talking about debugging, she showed WinDBG and SOS, right? SOS is the component. If you want to do anything debugging, .NET memory dumps or .NET code in WinDBG, you need to use SOS. You load it up and it has the commands. And along with the other components, really that provides the bridge. So WinDBG is like a native debugger. It only knows about native codes. Our code in the runtime is managed. It's gone through a JIT. There's kind of levels of abstraction that aren't there in native code. There's data structures that describe and all sorts of stuff. So that's the job of SOS. It's kind of like a plugin. But also you have the DI data access. That's providing a way for, given a .NET process, how do I get useful information out of it? Like, where's the location in memory I can find the list of all the threads that are running, because they're managed threads, not native threads. How can I find information about a JITted method? How can I find information about managed types? All these sorts of things. So that's data access layers provided there. On top of that, when you're debugging, say, in Visual Studio, you're doing F9, F10, whatever, all that sort of stuff, that's talking to the .NET debugging API. Again, Visual Studio understands native, but to control a .NET process, to be able to step through even something as simple as stepping through lines, when you're stepping through the actual assembly, you need to map that back via the IL to the original code that was written. You need to understand that relationship, because we don't want to step through in terms of assembly code. We want to step through in terms of our high-level C# code, which is not necessarily a one-to-one mapping of assembly. So there's quite a lot going on there. Platform adaptation layer is so that the runtime can affect program regardless of the OS. And then this part of the code handles, that's the theory behind the platform adaptation layer. So obviously for the longest time, .NET pretty much ran on Windows, but now it's Linux, and there's code in there to let it run on Unix and all the different OSs it supports. And then onto the APIs. So you might not know that the runtime actually has APIs. So I've sort of talked about one already. There's a debugging API. That's how any third-party and Visual Studio debugger can debug a .NET process. There's an API to use. It's inter-process communication. There's commands sent backwards and forwards. You move to the next breakpoint. All these sorts of things. There's an API that allows it to do that. And third-party debuggers. These are published APIs up on MSDN docs. It's known as iCore Debug, the debugging API. And then iCore Profiler is the profiling API. And essentially my day job is working with the iCore Profiler API, and it's what probably most people know it if you've used any profiling tools, obviously, but any APM tools. .NET APM tools will probably use a profiling API. It gives you the sort of access to a runtime process that those tools need. And one of the main bits that a lot of those tools do, and what certainly the tool I work on does, is actually rewrites your IL at runtime. That's sort of the secret code of some of those tools. That's how those tools can instrument your code without you having to make changes. And that's part of what the profiling API provides. So just as a sort of little tip, if you ever think, okay, I'd really like a job where some of this internals and this runtime stuff is like part of my daily job. If you ever see a job advert asking for knowledge or mentioning the profiling API or debugging API, that's probably your sort of secret way in, right? It's worked for me for the past 6 years. You certainly have to understand, in terms of one level of abstraction lower to work with the profiling APIs. But just to give a caveat, those APIs are COM APIs and you're writing code in C++. So if that's not your thing. So my job is split between the code I'm writing in profiling, which is C++, at the same time writing a managed part of, well, it's a bit of both, but certainly those APIs require knowledge. And if COM is a word that you don't ever want to hear in your professional life, then maybe stay away from that. But anyway, there's some APIs in there. And fortunately, and I think Microsoft, is not a coincidence, these are all versioned APIs. Microsoft agrees to support them. It's why there's a big ecosystem of third-party tools. In situations where Microsoft doesn't necessarily want to make all those tools, they've made these APIs available and they support them throughout all the different versions of .NET. On to the part that is the most focus of this talk today is sometimes known as the VM, virtual machine. That's the folder it's stored in, sometimes known as the execution engine. It's really the bit that hangs all the other parts together. It's the bit that executes first and then it will invoke the JIT. It's the bit that sets up the GC and gets that running. The other parts are clearly not trivial, but there's a lot of work going in the virtual machine side of the code. It's what's considered, I suppose, the runtime part of it. But what sort of things does it do? Well, quite a lot. So you've got your type system in there, generics. We pretty much take generics for granted, right? We've been fortunate in .NET to have them since .NET 2, so only if you were in the very early versions of .NET would you have not had generics, and maybe you remember array list and all the, the non-generic things. But anyways, we can write generic code. Maybe if you've seen other runtimes like Go, it took a while for them to get generics, and there was big debates about how they could make it work with the language. So we should be quite grateful that it's been in, if we like using or writing generic code, we should be grateful that it's been in .NET. But it basically makes everything else harder. Your types have to be aware of generics because types can be generics. Methods have to be aware of generics. Method calls are more complicated if you're calling a method with generic arguments, and so on and so on. The type system is also important because it's what gives us type safety. And if we didn't have type safety, I guess we'd be writing, dynamic code. And if you've ever done any dynamic code, you know the trade-offs there, right? We can rely on quite a lot of things in C# in terms of if our code compiles, we know something about it. Obviously, the built-in types, they have to ship with the runtime, so strings, arrays, all the primitives, those sorts of things. Span nowadays is another one that's added in there, span, read-only memory included in that. Loading types and classes, generally are types and classes loading as well, but obviously any other code has to deal with that. And there's, again, the guarantees, it won't load a type that doesn't meet the type system requirements. If you've ever had type load exceptions or those sorts of things, there is ways, not generally in writing in C# code that goes through a compiler, but if you ever, you can write whatever IL you want and pass it to the runtime and it'll have a go at it. So it has to be sure that it knows the classes fit in with type safety. Threading, we obviously have threading. We don't, probably nowadays aren't really writing, newing up threads and stuff. There's thread pools and much higher levels of abstraction, but they're all built on top of the threads that the runtime provides that aren't OS threads. So there's a whole level of abstraction there. Exception handling, stack walking, again, we probably don't like getting exceptions in our code, but if you ever used a language or runtime that doesn't give you decent stack traces or doesn't tell you, where an exception happened, you should be very grateful that, with the first-class experience we have in Visual Studio that pops up an exception and gives us the whole stack trace, and we can, jump to different parts of the stack trace. We can see variables in the stack trace. We can, all these sorts of things. A runtime provides quite a lot of that, and just the whole exception handling, the ability to throw and catch and all those sorts of things. we probably use quite often in our code. Event tracing, profiling, I've talked a bit about, but event tracing is quite a lot. So if you, again, the talk this morning talked about tools like .NET Counters or .NET Collect, or a lot of these tools are querying into the runtime and finding this information out. So there's a lot of information the runtime publishes about itself, of what it's doing. And just even something like p-invoke, right? I mean, maybe we're not using it directly, but it's there in almost everything we do. Calling out to native code, maybe from time to time we use it directly and put the DLL import and stuff. There's quite a lot of work there. So that gives us a rough idea of the landscape. So the first thing I'm going to talk about is virtual stub dispatch. Has anyone heard of this in the context of .NET? Few people, great. So everyone else is going to learn something new today. So virtual stub dispatch is, you will know it, you just won't know it's maybe called that. But let's say, so hands up who's got an iLogger interface in their code. Yeah, okay. And hands up who's got any interfaces in their code. That's everyone, right? I don't think many people write any code without interfaces. So we kind of take it for granted, right? We can do interfaces, the whole program to the abstraction, not the implementation. We can switch it out. Although actually we probably find that a lot of the time we might only have one implementation of an interface because it makes it mockable and testable and all those other things as well. So it's not even that we're always having multiple implementations, but that's there as well. So you have the kind of standard thing, you have a iLogger, this is a console one, you can imagine like a Azure table storage logger or whatever, event logger, there's different implementations, you might swap it out via DI or have your code set up. But it's called virtual because actually in the IL, actually this is more the metadata. If you were to look in IL Spy or some of those tools, IL DASM, they'll often put in, or at least the one I was using here, puts the method attributes as comments. So this is not something we see in our code, but this is what's behind the scene in the metadata, and it's talking about virtual. And then, so I like to think of virtual as like, essentially it's because the compiler can't guarantee where that method call is going to live at compile time because it's behind an interface. You have a method, it's given an iLogger interface. Now you could say it could analyze the whole program and see, okay, there's only one concrete implementation, so it must end up there. Yeah, that is true, but the .NET just-in-time compiler doesn't generally do that. It looks at just methods because that's quite expensive to analyze the whole program. And even if it could analyze the whole program, actually you can dynamically load types. So there's nothing to stop you doing plugins and assembly load from and all that sort of stuff to load another implementation of the interface. So essentially it means certainly at compile time and generally even at startup time, it can't guarantee, except in a few niche cases, where that method. So by the time the runtime executes a method, it doesn't really care about interfaces and that. It needs to know the place in memory where the code for that method is. And it needs to be able to go there, having put the parameters on the stack or whatever the stuff it does before. It needs to basically jump to that location and that code needs to execute, does what it does, and then jump back and return values and all the things it does in a method call. So it needs to have a concrete thing, and that's what virtual is all about. So if we look at this example here, we've got an iLogger method. So in the one that isn't highlighted, it's taking a concrete implementation. The compiler can figure all that out. It knows it's a console logger class. It can say, right, you just need to call the console logger class log error method. That's fine, there's no issues there. But if we're talking about a method with a interface, it needs to know which implementation of the log error function it ends up as. Now, this is a slightly confusing example because actually, when you new up a class and then straight away call a method, that's something the JIT can figure out because you've literally just created the object. So it's smart enough to do that. So it can do some, and that's something called devirtualization that we'll get onto in a minute. But generally, when it's looking at the something went wrong method at the bottom highlighted, it doesn't know until the method's called at runtime where it needs to jump to actually execute that method. And so you see that in IL, if you dig down to that, it uses the callvert instruction. It actually uses the callvert in the concrete case because the callvert also does null checking, if you've ever looked at that. So it's sort of a safety thing because the callvert, there's actually a call instruction that can be more efficient, but it doesn't check for nulls. But certainly in the case we're looking at here, it's callvert. So that's why it's virtual. It doesn't know at compile time. But something else we need to understand about this is whenever you call a method, sorry, not whenever, in most situations you call a method in .NET, between the call sites where you write foo and pass in the parameters, and the callee where the method actually executes, there's generally a stub. And stubs are like everywhere in the runtime. If you want proof, that blog post is 11,000 words. I wouldn't recommend reading it all in one go. There's a table of contents, but it shows all the places. P-invoke goes through stubs. There's stubs that handle moving from managed to native code and marshalling and a few other things. There's stubs when you call generic methods because it needs to know about generic arguments because we'll do generics in a minute, but there's stubs in a lot of places. And so I think of stubs as like a bit of housekeeping, a bit of fix-up. It's not two method calls. This is all one method call. The stub in the middle is like doing a bit of work, moving a few things around, and then a straight jump, literally a jump assembly instruction to the place. And it does some fix-up. So that's what's going on with stubs. So this person, Simon Hall, I came across his name because there's something called the Book of the Runtime. And if you want to get into the .NET Runtime and you want a free resource, I showed some books earlier, but on the GitHub repository, BOTR, Book of the Runtime, is under their docs folder. It is written for runtime engineers by runtime engineers. So it's not an introductory thing. I often read one of these pages, scratch my head a bit, make a few notes, come back a week later and then understand a little bit more and read it, So it's not that they're not well written, there's not nice diagrams, but they are written with an assumption that you're already working on the runtime and here's how another bit of the runtime works. So there's a bit of knowledge maybe to get into them. I've got some good mileage out of basically understanding enough about a Book of the Runtime page to feel I can write a blog post to explain it to people who don't want to read the Book of the Runtime page. So anyway, but he wrote the page on virtual stub dispatch and he was so pleased with what he did, he put it on his LinkedIn. I mean, you would, because virtual stub dispatch is every time a method, or maybe not every time, I think they've done some stats in some measurements elsewhere. 95% of methods when we call a method involving an interface go through virtual stub dispatch. There's a few times that it can go directly. But so in the .NET 2 timeframe, they redesigned it. And this is the sort of stuff that the runtime engineers have to worry about, right? So there's a trade-off, performance, but also memory locality, memory density. If they had something that made all our code run faster, but every time the .NET app started up, it used twice as much memory, then we'd probably be a bit annoyed, right? So they have to do these trade-offs. And we'll come on to the second, the stubs of small, because they don't want to make have a bad trade-off in terms of memory. But they did improve it. So anyway, if I'd done something significant like that, I'd be putting it on my LinkedIn, that's for sure. And you look at the other stuff, he did quite a lot of interesting bits on the .NET Runtime, probably, 10 years or so ago. So virtual stub dispatch, the way it works is step by step is this. First time it comes in, it's basically that I don't know, right? It doesn't know where that method exists, the concrete method. It knows the object you're calling it against, so it can do some lookups, because the runtime has something called a method table. Attached just in front of every object on the heap, there's a pointer to the method table. And the method table is basically which type, class or struct or whatever, this object is of. And that's why we one of the things it enables is reflection, the strong, the really rich reflection that we get in .NET, but it also helps with type safety and a few other things. But that's an overhead. That's why we talk about, say, we get into classes versus structs. Every class object instance, on the heap has that overhead because it needs to be able to reference back from the actual data of the object to say which type is this. And that obviously also helps with things like when the runtime's doing class hierarchies to know which method to call in the hierarchy if you've overridden or inheritance. And it also helps with interface. So the first time is like, I don't know. So it has to fall back to step 4 in this case, which is basically go and find out where this method lives. I've got an object, I know the method of the interface, and remember that an object has its own methods, a type has its own methods, plus the ones that is implemented for the interface. You can have multiple interfaces implemented to a class, you can explicitly implement interface methods, and you can have methods that just exist on your type that aren't anything to do with the interface. So it has to figure all that out. Then you throw in, does this class override a base class, and is there abstract classes, and there's a bit of stuff to calculate there. Once it knows that, it starts to build up the stub. And there's an assumption it makes that basically there's a high chance that next time you call the same method, you might call it with the same type of object, not the same instance, but the same type. So that's the monomorphic case 1. I'm going to assume that I believe they've done some analysis of programs and some other things to say that's kind of common. And it goes back to what we were saying at the beginning. We might implement an interface just for the sake of having that abstraction so that we can make it unit testable. In our production code, there might only be one concrete implementation of that class running. There might be two if you're looking at the test code. But so that's why that it's kind of, let's optimize for the best case scenario, which is there's one implementation and it's the same one I saw last time. But we know that's not true, right, all the time. So it has to have a fallback. So it then has to fall back to the polymorphic, right? There's two implementations of this interface. I need to look at the object every time and decide which one of those two it is and dispatch to the right place. And one thing worth pointing out in generic resolver, it did something called backpatching, so that the first time it comes in, it goes to the resolver straight down to 4. But next time, it doesn't want to do that. So it backpatches, which is like rewriting some location of code in memory to set the object so that next time it can say, right, is this the same object? It does a comparison. Another way of looking at, if you want, and this is from the book of the runtime, is this is a different path because it can change. And it can actually say, look, I made a guess the first time based on the fact I thought you'd always call it with this concrete implementation. But you know what? In the 99 times since then, you've called it with a different one. I think I better adjust my best guess because I'm always falling back to the worst case scenario. So these things are changing, and then it will redo the backpatching to have, but it doesn't want to get in a case where it's always backpatching, so there's a bit more logic there because you could get in a bad case where it's always swapping between two or things like that. So again, these are things they need to worry about because it wouldn't be great if our method was quick the first time, but every subsequent time it was slow. So these things have to adapt. And in fact, in the debug version of the runtime, you can turn on some stats and they're able to run a program and see things like effectively cache hits and misses. How many times am I going through the best case path? How many times am I falling back? How many times am I changing my guess and repatching and so on? And this again is all back to the Simon, the guy I showed previously, his page. This was all different in .NET 1 and they updated it in .NET 2 for performance. And part of actually, the other thing they did is you can have two call sites and they can go through two different stubs even though they end up the same place, because basically they determined that the call sites could be calling the same method but with different usage patterns. So again, this was a trade-off. They said, right, we'll have more stubs, we'll keep them small, we'll have more stubs, but it gives better throughput. I'm not going to show a lot of assembly code because I can't understand it all, let's be clear, but I can at least understand this. So this is the kind of monomorphic case. What it's doing is a comparison of the EAX, which is like the pointer of the current object, comparing it to expected. This is like, I've seen this before, are you the same type I saw last time? If you're not, jump to the failure case, the worst case. I need to adjust my logic or I need to fall back to something else. If you are what I expect, because I've seen you before, then jump straight to the target. So we see that actually it's two assembly instructions. They've got it down to two assembly instructions for the best case scenario. And again, this is the sort of stuff that the runtime engineers have to worry about. If that was too big and we had lots of these stubs in memory, and you can imagine how many places in our code we call different call sites calling different methods, a lot basically. But this is all overhead, so they would like to get rid of it. So that's the opposite of all this is devirtualization. And if the JIT can actually say, do you know what? I don't need to do any of this. It can save the two extra, even in the best cases, instructions. Part of it is also, it's not just the best case, but like the first time through, when I said it has to fall back, that's slow. So that first time through equals slower startup. So that's why this is also important. So there's been some work. This is from a little while ago, back in 2017. I think the issue is still open. They're trying to say, is there more and more situations we can skip all this out? It's a great mechanism. They've tuned it over time. It's about as efficient as it could be when you're talking two assembly instructions. But you know what? Code would be even faster. And this is when we get into like tech in power running at, million frames a second, 10 million requests per second, in fact. That sort of level, right? This thing starts to matter more. So sometimes some places may not use interfaces because there is a cost overhead. You have to time it to prove it's really a difference for your situation, but there is a cost overhead for interfaces. So we've covered that. So value types. I'm sure these are familiar to most people. Who's ever had an interview where you've been asked about structs versus classes, right? It's pretty, yeah, I think it feels like hard to get a .NET job at some point in your career where you don't get asked that. And there's a whole thing about, do they live on the heap, do they live on the stack, whatever, people, you read it on Stack Overflow, get the answer next time you have a job interview. But the point more is about what they're implemented. So the things that we do know about structs and versus classes is there's no method table overhead for a struct. So they compact more in memory, and that's one of the main reasons people end up using them, because the data needed for a struct is just the data for the fields of that struct. I think it's one thing in terms of like taking stuff for granted, right? We changed the struct keyword, the class keyword to struct, right? It's one word change. There's quite a lot of stuff that implications for the runtime is quite big behind the scenes. So yeah, if you had an array of structs, the data in the array would be literally struct 0, struct 1 packed in there, the fields of that within that. If you have an array of classes, what you've got is an array of references that point to the actual reference living somewhere else. They might be all near each other if you allocate them together. They could be all over. The GC can move things around, compact, whatever. But it's still that extra level of indirection, that reference to go from what's in the array, which is it does mean that reference is easier to handle in some ways because a reference is always the same size because it's a pointer to somewhere else. But structs give us, if you care about packing things in memory, if you care about the efficiency of not having that extra level of indirection, that's why I think in games and things like that, or you go and look in the Kestrel source code, that's what's running in the Tech Empower benchmarks, that sort of thing becomes more of an issue. And then there's also the discussion around allocation and, it causes GC. Generally, structs can be allocated on the stack, except they aren't. I'm not going to go into that whole thing. As I said, look it up on Stack Overflow, but you can a lot of the time assume they are allocated on the stack, which equals no GC pauses. But as I said, we take it for granted. But so I counted a while back. There's 63 places in the runtime. No, 64. 64 places in the runtime and 23 issues or something. I don't know. Where the runtime code has to care whether the type, that it's dealing with is a value type or is a struct or is a reference type. And a lot of that you can see some in like. Reflection in invocation of class there. But a lot of that is the first case, which is boxing, right? Boxing is one of the things it has to worry about once you get into value types, because you can box value types into an object and it has to deal with that, and that's what the runtime helps us out with. But another place is when you're calling a method. If you're calling a method with reference, it's when the word comes in, right? By reference, you're passing a reference to an object. That reference is always the same size on 32-bit or on 64-bit. You just pass, in effect, a pointer, and then the method that on the callee on the other end just takes that reference and then can access the type. Struts pass by value. It needs to physically put the contents of the strut. And at this level, we're talking about on the stack or as an optimization registers. So there's a certain amount of registers. It varies, again, per CPU. There's rules about registers. Some registers are reserved. So you see in the top case here, I haven't got the laser, but you see in the top left here, the this parameter. So that's passed around as like an implicit parameter. So we call a method. We don't ever pass the this parameter, but if we're calling an instance method on a class, that's done for us behind the scenes. The reason in this case, if you haven't picked it up yet, what's happening is all the arguments are being shuffled one left. So this pointer is being dropped and it's shuffled one left. If you want to find out what's going on there, you can read the issue. It's one of my favorite things I discovered. It's called a shuffle thunk, and its job is to move everything that way, because by the time the method's called, this argument needs to not be there. And it's to do with delegates, and I'm not going to go into, if you want to come and ask me later, I can explain a bit more. But the point is, this is the stuff it has to deal with. And it would like to put as much possible in where I've highlighted it green, right? That's registers. Registers are faster than stack. So when it gets down to moving stuff around, if it can reuse registers, great. But there's rules about which registers can be used. Certain data types only fit in certain registers. You have special purpose registers. They're different on x86 versus x64. You also have to respect the platform or OS running on them, because there's some rules about registers and something that's known as ABI, Application Binary Interface, which is how do methods get called on this platform. So that's different on Windows versus Linux, even under x86. So complexity all over the place. But yeah, just to give you a sort of idea. So it's shuffling these things around because when you go from a call site to a callee, the callee of that method expects things to be in a certain place. It needs to know the rules of where it can get the parameters for that method. It knows what type of method it is. It knows it's got 3 arguments, but it's the job of the call site to put things in the right registers if it's a value. These things are sort of laid out in something called ABIs, Application Binary Interfaces. Another thing about generics, this might be a bit more known, but if you have a generic method, simplest one possible, literally storing a value. It's a wrapper, right? We've got one field of type T, we've got a store method where we pass in T and it stores it, right? It seems a bit contrived, but I'll show you in a minute there's actually real world examples for this. The point is if T is a reference type, it does sharing, right? It can basically say all reference types are, in terms of what I need to worry about, are the same size. So I know the location, I can store them in the same location. I don't care whether it's your own class or a base class, library class. If it's a reference type, easy. So it does shared. And that's to stop there being an explosion of methods. If it did a different method for every time so we have like iList, right? That's generic. If every time we need up a list for a different type, so the runtime cares enough to make sure there's not a lot of extra methods, and it can do that by sharing all the method implementations at the assembly code level for reference types. It can't do the same for value types. So this is primitives. Same applies if it was our own struts. So that's partly it's because they're different sizes. So an int is different size than a double. So it can't make assumptions about even something as simple as storing a value because they need to be stored differently because they have different physical sizes. Even if they're the same size, we sort of see a bit here, there's different assembly instructions that make sense. So this is like a vectorized version at the bottom where it can store the double more efficiently. The JIT cares about this because we want our code to be as fast as possible. It's some of the stuff the JIT does for us. We don't probably think about it, right? I just want to put whatever I want in a list. But actually the JIT's doing some work to make the double version as efficient as it could be for doubles versus the version for floats versus for ints. But it does mean that it has to create different versions. So this is, there'd be 2 different versions of this store method for both these cases. Why this is important? Because actually you can kind of use it as a trick. And I suppose some people have heard of Ben Adams, right? Have people heard of, if you want to learn about some really good performance tricks, look up Ben Adams' GitHub profile and see some of the PRs he's done in the Kestrel web server, like this one here, in ASP.NET, sometimes in the runtime. It's fair to say he knows what he's talking about with performance, and he's submitted many, many PRs, and quite a lot of them have what helped push the Tech in Power up. If you've seen the Tech in Power results they publish from time to time showing .NET, basically .NET competing with others. I think it's one of those ones that's at the level of they're maxing out the network card, right? There's a few that are sort of all within a kind of space for each other. It shows that actually, maybe we're not writing code that needs to run at 10 million requests per second, but it's quite nice to know that we're working on a runtime that could be used for that if we'd ever need to. But he uses this thing, David Fowler, I'm sure many people know, calls it type system abuse. He likes to call it working with the type system. So you can actually use this trick of the JIT having to make a different version of every generic method. You can use it to get more efficient code. And he did that. So he literally, it's very similar to the code I wrote a few slides back. He wrapped a frame in a strut frame adapter that pretty much you can see stores the frame and then passes through the methods and then obviously wrapped it when you do it. And this 39,000 extra requests per second. And the reason it can do that, going back to the previous slide showing ints versus doubles, is for every different struct it sees, the JIT makes a different method, and because it makes a different method, it can optimize it just for that code. So that can be the most efficient version. So we saw the one of ints and doubles, it was making them more efficient based on that. There's other stuff the JIT can do, but it can specialize because it's not making a kind of generic method, if that makes sense, with struts. I'm not saying wrap every class in your code with a struts, please don't do that. As you can see, I mean, it's a nice number, but it was already at 1 million requests per second, 1,021,000. It went up to 1 million, we're talking you need to be at quite a high level performance before this really helps. But anyway, it's part of what the runtime provides was giving us this flexibility, because not all runtimes have the ability of value types, right? I'm not going to start naming names, but there is some that don't let you create your own value types, or still trying to get that in their runtime. So it's quite nice that .NET CLR gives us this option if we need it. Having said all that, they want to have universal shared generics, because obviously there's a cost for all of this for the runtime, and they'd like to make the ability to have more generic methods, because we don't always need that extra performance. And so, yeah, there's an idea. It's, again, this is from a little while ago, me basically asking what you're talking about, what is universal shared generics? But the idea is that actually there's a cost. And the reason it matters more is because of ahead of time compilation. This specialized version of the code has to be jittered at runtime. That doesn't help. So when you want to have generics and ahead of time compilation, as I said, generics makes everything harder in the runtime. This is the sort of thing they might need to go down the route of not having specialized. Even though it gives a nice performance boost in some cases, I think that ultimately for ahead of time compilation, and that's, you can see why Mono's had it there for a little while as well. It plays a part. Okay, so on to another thing of value type, so boxing. So we generally say boxing is bad, right? You want to avoid it if possible. You don't want to always be boxing your struts into an object. But even in that case, the runtime tries to make it as efficient as possible. Clearly, those more objects go on the heap, and the garbage collector has to do more work. But the garbage collector is a pretty impressive bit of code, and there's, you know, it's not like all garbage collection is slow and pauses your application. There's many times it can clean up huge amounts of memory on the heap without your program, you know, having a beat or whatever. So even for something like boxing, which is considered you shouldn't be doing it excessively, they've at least tried to make it as efficient as it could be. So it'll try and inlining. Inlining is like the first thing the JIT does, because if it can inline a method into the calling method, then it's just more efficient because you haven't even got the mechanism of a method call, and it can then do other optimizations after that. But it generally only does that for things it knows about, ints, int64s, primitive types. So there's assembly helper. So one of the things you see quite a lot in the runtime is handwritten assembly code. Because if you think, right, so the options for the runtime is write it in C++, so that's okay, you can rely, but then you're relying on the compiler doing the right thing. You could write a lot of runtime code in managed code, and then you need the JIT to JIT it. But the JIT isn't necessarily thinking too much about JITting the sort of code that exists in the runtime. It's more worried about JITting the code we all write and making that efficient. And certainly when they were first making the runtime, they were making it at the same time as the JIT was being made. So there wasn't, you know, so it's kind of chicken and egg thing. So there's times where there's handwritten bits of assembly just because it's very specific what they want to do, or because it's performance, or because they can't write it any other way because it won't do the most performant code. And then it falls back to some C++ code. So again, there's this sort of idea a lot of the time in the runtime like a fast path. There's many times that the code can allocate without needing to trigger a garbage collection. If you're in any GC talk, or certainly it's talked about this one as an idea of segments, and if there's space in the current segment, allocation is really just bumping a pointer to make space for the object. It's only when it runs out of space in the segment, then the GC has to get involved and decide whether to allocate more segments or do a garbage collection and so on. So a lot of the time, allocation, not really allocation, it's just bumping a pointer. Sometimes it can fall back to those. To give an idea of some of this code, essentially, is copying via pointer. If you've ever done any C++, this is like, you know, the sort of stuff you have to write in C++. Right? But it's basically, if it's a certain size, so 1, 2, 4, or 8, it will just literally copy. So we're talking about here, you've got your strut, and it's ended up being boxed, and it needs to create a chunk of memory on the heap and put the contents of that strut into the, if you like, into the box. I guess that's where the name comes from. So it needs to copy the contents of your struct at that time, turn it into, it would have already created an object that represents the box version of that, but it needs to put the data in. And then it has a fallback if it's not one of the nice cases of the right sort of size, because it can't just do it via pointers of unsigned 32 and so on. But it also has to tell the garbage collector, if you know with struts, you can actually have a strut that has a reference, and this is when struts get complicated. You can have a strut that contains a field that is a class, right? That's, you know, you can write code like that. So if it's then making a copy of that, then it has to tell the GC, look, hey, I've made another reference to a object. You need to know about that because that's going to affect how you do garbage collection, right? You need to know there's now two references, and only when they both go can you clean it up and all that sort of stuff. So that's what it's doing. This is like the lowest level. And even then it's doing some interesting stuff with pointers and oh gosh, yeah. Don't you love C++? Although actually you can write, nowadays you can write C# code that looks not too dissimilar with all the new features they keep adding that lets you write something more and more like C#. It's also quite nice that basically it's, some of the code in the runtime is readable even if you're not C++, right? We can all read a while loop and stuff like that. We can have a rough idea of what's going on. Unboxing is the reverse. You don't tend to unbox as much as you box, really. It's normally a one-way thing, but you can unbox if you want to. And again, the runtime tries to do the best it can in all these situations. You probably shouldn't box because it's overhead, but if you're boxing, then you probably shouldn't unbox because there's more overhead, but it still made it as quick as it can across the runtime. Another thing to think about with structs is that essentially, when you pass a struct, it's kind of like, so you have an instance method on a struct. It's kind of like you're passing it with the ref keyword, because when you call an instance method on a struct and it, changes the value of a field or whatever, you'd like it to operate on the struct you called it on. You wouldn't like it to be on a copy, right? Because then you'd lose those values. So again, runtime, we don't care, right? When we call a method on an instance method on a struct versus a class, we're not worrying about what's going on, but the runtime has to figure some of this stuff out to make sure it does what we'd expect. And another one to finish with on structs. So you have a struct, you might override toString, right? Think about what happens when you box the struct. There's a toString method on object, right? So you would like your toString method to be called, not the kind of standard one, the built-in one on object, which basically prints the type name, right? If you've ever seen that. But it gets a bit complicated. So as we talked about before, a struct looks like this in memory. When it's boxed, you've got the extra stuff, the method table, the object header, and then the data at the end is the same. That's basically how it does boxing in a pictorial form. When you have an object, the pointer of the object is actually to the front of the method table. So it can then do that kind of lookup quite quickly. It could be behind the method table, but the runtime chooses to be between the object header and the method table. But essentially it means that by the time you've called the toString method, the pointer actually needs to be here because that toString method will make assumptions about the layout of the struct. So this is getting way into the weeds on like structs, but essentially, even if you're boxing structs, the runtime, and I said stubs were everywhere, there's a stub that fixes up that pointer so it can just, so again, if we ever meet a .NET Runtime engineer, this is stuff we generally don't have to worry about. We should probably thank them that we can just write code in the most simple way. And it does the right thing and it does it efficiently. Okay, on to the last section that I'm talking about today, tier compilation. People heard about this. This has been around for a little while in .NET Core. Few people, yeah, okay. So it's been in the runtime since 2.1. They turned it on by default since 3, I think. Anyway, certainly in .NET 5 and 6, it's on by default. And the basic idea behind it is that the problem with just-in-time is it's just-in-time, right? I mean, not necessarily a problem, but it's the nature of it. But if you have method A that calls method B, that calls method C, that calls method D, they all need to get jitted before method A can run, because as it hits the point in method A that it needs to jit method B, it goes and jits it, and so on. So jitting can be a problem for startup. If you've ever used like NGen and things like that, there is ways around it. You can pre-compile that, so it doesn't have to do that. And certainly the base class libraries and the runtime is shipped with that all done, because otherwise startup would be really slow. But our code generally isn't, unless we've made the step of doing NGen previously, now ready, R2R ready to run is the kind of precursor for that. So you can do that. It obviously matters, startup matters more in like a containerized world, right? Or Azure functions, those sorts of things where we expect things to be running quickly. If it's a long-running process on a server, maybe starting up in 5 seconds versus 2 is not such a problem. If it's a function that takes a second to run, then that starts to become a problem. So this whole startup is something I worry about. And again, another stub. When code, and the way it works is just in time, is it puts the stub into place. And the first time you call a method, it hits that stub. And that stub's job is then to JIT the method and then rewrite the stub so that next time you don't go through the stub, you go straight to the methods. That's what the stub's there. And so you see after JITting, we've lost the pre-stub. Pre-code fix-up has to still exist for a bunch of scenarios and can also help with things like generics and other places where we always need a stub. But there is a way to go straight to the native code. So yeah, the pre-stub is what's happening the first time if you ever, and you can sometimes see this if you debug code, some of these things show up in a stack trace, pre-stub. With tiered compilation, what they've done is they've left some of that in, so they've left the pre-stub in, but it's now got a counter. And the basic idea of tiered compilation is this, is that actually a lot of methods don't need to be heavily optimized the first time. Right? If that method only runs once, why spend relatively a long time in the JIT doing all these really impressive optimizations if it's only going to execute once? But you know what? If that method is executed 10,000 times a second, you'd really like the most optimal version of that method. So what tiered compilation does is it breaks that dependency, says, right, the first n times, I believe it was 30, but anyway, there's a counter, it can be a bit more intelligent than that, but it says, look, we'll do the quickest JIT possible the first time. It's called min-ops, minimum optimizations. Don't try and do anything fancy, just get that code out there as quickly as possible. It's functional code, there's no doubt about that, but it's not the most optimized. Do that, put a counter in, see how many times the method's called. If it becomes hot, on a background thread, re-JIT the method so it's not blocking execution, and then in quite a clever way switch it out, because you have to worry about if the method's executing and there's a synchronization thing going on there. But once you've done that, then switch it out for an optimized version. And that really helps startup time, because you can do the minimum work first time and then worry about it later. And it also helps them do extra analysis, because they can actually, I don't know how much this is implemented, but the idea is actually you can do a second attempt, and then maybe down the line you could do a third and fourth attempt. Once the mechanism's there might be scenarios you say, look, another type's been loaded, it changes our idea of how the program's working, let's have another go at optimizing these methods. So I believe at the moment it's just tier 0 and tier 1, but there's, in theory, the mechanism's there for more. And then, yeah, with the optimized one, we now have, again, and it still keeps around, so you've got the optimized native code, so this is after it's done the tier 1, which is the more optimized version. It's now the method is going to, every time it's going to be called, it's going to go to the optimized one, but it still keeps the original one around, and there's various scenarios where they might want to go back, because actually there's a potential that they made a bad decision, right? There's some flexibility there. And it also relates to things that I want to work on with, like the profiling API, where there's the ability to re-JIT methods, and a bit of stuff with sometimes when you're debugging, there's a way it can change the optimization of methods. So there's a few cases where it needs to go backwards and forwards. And this is part of a larger initiative. I think this is more of a design document. I've not seen how much of this has yet been implemented, but the idea is that, yeah, re-JIT there. The point is that actually there might be times where, even, we talked a bit about generics, you might see a generic method, you might want to optimize the int version because you see that being called loads, but the version for string is not called so much, you want to leave that as is. So yeah, they can, the mechanism behind this is code version, it can allow more, but at the moment it's mostly tier 0, tier 1. So that's it of a brief introduction to the runtime and the performance. Yeah, Book of the Runtime is really a great place to start. I've written a bunch of blog posts about internals, but also some of, like, if you want to find your own way through this, right? So resources, how to explore the runtime, some tools, and other presentations from other people. So there's some blog posts to get started with, but thank you. Thank you for coming.